Welcome. In this video, we are going to look at evaluating integrals, and we're going to look at some strategies that we would try to employ when we're dealing with rational integrals. So in this first example, we're going to do two examples in this video. This first example, we have a rational integrand. And one thing we'll notice about this rational integrand is that it's an improper fraction, meaning the numerator is a larger power than the denominator. So a strategy we use when we're dealing with improper fractions is to divide that, simplify it a little bit. So setting this up, my numerator is my dividend. And remember, when we set up our dividend, we want to list all terms in descending order. So I'm looking at this, I've got quadratic, linear, and then constant. And my denominator is my divisor. So I'm going to be dividing in 3x plus 2. So 3x goes into 3x squared. If I do that division, that gives me x. I'll take that x in my quotient and I'll multiply it by my divisor. That gives me 3x squared plus 2x. And whatever I've put down here, I will be subtracting. Now, if I've done this correctly, the product from my quotient and my divisor should always be exactly the same as that term I was dividing it into in my dividend. And those first two terms, when I subtract, are always going to cancel. So 3x squared minus 3x squared, and then I have negative 7x minus 2x. So negative 7 minus 2, that gives me negative 9x. We bring down any following terms. So let's look at this again. How many times does 3x go into negative 9x? And what I'm doing there is I'm saying negative 9x divided by 3x. That gives me negative 3. So again, I will take that negative 3, multiply it by both my terms in the divisor and write them down there. Negative 3 times 3x is negative 9x, and negative 3 times 2 is negative 6. Again, subtracting, the first two terms cancel, and I have 0 minus negative 6, which minus a negative, that's going to give us a plus 6. So now I have a quotient, what I might refer to as Q of x, and a remainder, R. And what you should have learned in your algebra class is that original polynomial dividend divided by some divisor, that is equal to a quotient plus my remainder divided by that original divisor. So what I have here, this original integral, I can now rewrite that and say, well, this is the integral of that quotient, x minus 3, plus my remainder is 6 over the original divisor. So we want to integrate all of that with respect to x. All right, I'm going to clean this page up. So again, all I've done is I just used basic algebra skills, division of polynomials, so that I could write these as smaller, easier to deal with terms. And now, if I look at integrating each of these terms, integrating x, that's going to give me x squared over 2. Integrating negative 3 will give me minus 3x. And my integral here, for this fraction, I'll need to do a u substitution. So I'm going to write that out. I'm going to go ahead and pull the 6 in front. So 6 times the integral 1 over 3x plus 2 dx. And to do this, or to find this integral using u substitution, I'm going to let that denominator equal u. So I'll say let u equal 3x plus 2. And then that, of course, would give me that the derivative of u with respect to x is 3, or 1/3 du equals dx. So I have 1/2 x squared minus 3x plus 6, and now my integral looks like 1 over u, and then that dx is equal to times 1/3 du. And of course I can take that 1/3, if I have 6 times 1/3, that's going to give me 2 du. So the integral of 1 over u, this guy right here, is equal to the natural log of u. So this is 1/2 x squared minus 3x plus 2 times the natural log of the absolute value of u plus c. And we're almost done with this problem, but we have to have all of the variables the same. Since we started with x, we're going to end with x, and we know what u is in terms of x. It's 3x plus 2. So this is 1/2 x squared minus 3x plus 2 times the natural log of the absolute value of 3x plus 2 plus c. And it is important that you use absolute value bars here, because depending on what x is, the argument of my log could be negative, and we can't take the logarithm of a negative value. So we have to use absolute value to ensure that regardless of the variable, this argument stays positive. And of course, because it is an indefinite integral, we need to write plus c. All right, I'm going to do one more example in this video. For this integral, we're dealing with a rational function, and we have a square root in the denominator. We have a number squared, a squared, minus a variable squared, x squared. And one thing we should notice is that this denominator looks like a couple denominators that we see in our table of integrals. Okay, a squared minus x squared. So we have a constant squared minus a variable squared. So one thing we want to look out for, considering our table of integrals, is recognizing when that pattern occurs, when that might, ding a bell in our head and let us say, hey, let me go look at this table of integrals and see if this is anything like listed in there that I might be able to use to help me solve this. So I'm going to pull in 2 integrals from our table now. So looking at this, you'll see, if you look at these tables, and I actually pulled in more than 2, but you'll see we have a quantity squared, a constant squared plus a variable squared, a constant squared minus a variable squared. We have the plus under a square root. We have the minus under the square root with also an x variable in front, and then here's x squared minus a squared as opposed to a squared minus x squared. All right, so thinking about that, and remember, a represents a constant value. What I notice mostly looking at this is I see we have a constant takeaway of variable. And that lets me know that, hey, I might want to split this up, separate it, manipulate it in a way so that I have just a constant in the numerator. Okay, so noticing right here in the numerator, we don't have any other variables. This is just like saying we have a 1 in the numerator. All right, so we've identified that we're going to probably use integral 16 here. So let's look at how we're going to do this problem. All right, so since I have only one term that's all grouped with the square root in my denominator, I'm going to separate this. I have the integral of 3x over the square root of 1 minus x squared. And of course, because I have that 3x, I can pull the 3 in front and just have x there, so dx, plus the integral of 2 over the square root of 1 minus x squared. And that 2 can also come in front, leaving me with a 1 there. And so at this point, that dx could slide right into the numerator and it would look exactly like number 16 from our table. However, the first integral we see here, that is not one of the patterns. So we need to develop another strategy or come up with another strategy. I'm going to use u substitution. In order for me to do that, I'm going to rewrite the way this integral looks a little bit. This is the integral 3 times the integral x times the quantity 1 minus x squared to the negative 1/2 power dx. And of course, we have other information here. I'll deal with that for my second piece in a minute. Now, here we'll use a u substitution. I'll say let u equal 1 minus x squared. And that gives me that the derivative of u with respect to x is negative 2x. And that can be manipulated to give me negative 1/2 du equals x dx. So I see my x dx, and I see my u value in there, 1 minus x squared. So the integral here that I'm solving, 3 times the integral, I have u to the negative 1/2 power, and then x dx is equal to negative 1/2 du. So I'm going to take that negative 1/2 and put it in front. Now I have negative 3/2 of the integral from u to the negative 1/2 du. So I can integrate this using my power rule. The negative 3/2 will remain. U to the negative 1/2, if I add 1, that gives me positive 1/2. Dividing by 1/2 is 2u to the 1/2. So this first term turns into negative 3u to the 1/2. And we still have to deal with this piece up here that we had. So let me magic that back onto the screen. So you students of mine haven't really had much experience using these tables. One thing we want to notice is we have a constant squared. This is the same as if we had, say, 1 squared in there. So this value for a is a 1. Technically, that means there was a 1 there. So if this had been 16 minus x squared, we would end up with a 4 right here. But it's not, so we don't. That's going to be a value of 1 for a. So what this integral looks like is I have plus, I'm just pulling that down right here, 2, and using my table, that is sine inverse of x over my a value, which is 1. And of course, we're going to have our plus c at the end. So pulling that down, I've got 2 sine inverse. It just simplifies to x plus c. We're almost done, but we need to put my x's back in for my u value. So of course, u is equal to 1 minus x squared. So I have negative 3, and that's going to be the square root of 1 minus x squared plus 2 sine inverse of x plus c. And that's my final answer there. So just to recap, I did 2 integrals in this video. The first one, we had to use long division. And the second one, we again separated that rational integrand, and we also used u substitution and a table substitution. As always, email me if you have any questions.